Okay, for section 9.4 day 1 we are looking at mathematical induction. It takes a little time to get used to, but I think once you get used to it, it won't be too bad. It just takes a little getting used to. Alright, so we're going to look at two problems. They're similar problems, just both doing mathematical induction to prove something. It says, use mathematical induction to prove the formula for every positive integer n. And here's your formula. That 3 plus 7 plus 11 plus 15 plus following that pattern will always give you an answer of n times 2n plus 1. Like for example, this is the second number in the sequence. If you plug a 2 in for the n's, you would have 2 times, let's see here, 5, which is 10. Add the first two numbers together, it's 10. So that's what that's saying. And then another one, same thing, use mathematical induction to prove this formula, where 25 plus 22 plus 19 plus 16 plus all the way on to this, and this is just the pattern, will eventually give you an answer here. Where if you added the first two numbers together, I see it's 47. You plug a 2 in for both of these and multiply it together, it'll give you 47. So to show it, just prove that it works. Alright, so to prove it using mathematical induction, we are going to do the two things that you need to do. The first thing that you have to do is show that the sum works for the first term. So you need to show that s sub 1 is actually 3. So you simply need to plug 1 into the formula, and you would have 1 times 2 times 1 plus 1, which of course is going to give you 1 times 3, which we know is 3. So it works. The second thing you have to do is say, assuming that s sub k is equal to 3 plus 7 plus 11 plus 15 plus all the way out to 4 times, now I'm plugging k in, so this would change to 4k minus 1. There's the kth term. Remember what that stands for, the sum of the first k terms. That would be the first k terms. This is going to equal k. Remember the formula says you should just be able to plug the number in, so this would be k times 2k plus 1. So assuming that that's true, I need to show that s sub k plus 1 is going to equal, s sub k plus 1 would mean just plugging k plus 1 in for the n's up here. That would be k plus 1 times the quantity 2 times k plus 1 plus 1. So basically saying, assuming that s sub k is this, I need to show that s sub k plus 1 is this, and if I simplify it, it would be k plus 1 times 2k plus 2 plus 1, or plus 3. So assuming that s sub k is equal to this, I need to show that s sub k plus 1 is equal to that. Alright, so here's how I do it. So s sub k plus 1, if you think about what that means, it's the sum of the first of that many terms. Well, I know that s sub k plus 1 would technically be this. It would be 3 plus 7 plus 11 plus 15 plus all the way up to, here's the k term, 4k minus 1. And then it would be plus, the k plus 1 term would be 4 times k plus 1 minus 1. If I look at that as the s sub k plus 1 term. Hopefully that makes sense to you. Here's the first term, second term, third term, fourth term, blah, 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 blah. The k term, k plus 1 term. Adding all those together would give me the sum of the k plus 1 terms. Alright, well, I know what this is equal to. It's what I have written right there. It's 3 plus 7 plus plus all the way up to 4k minus 1. This is s sub k plus a sub k plus 1. This is actually the specific term number. So here's the sum of the first k terms plus the k plus first term. Adding those together would give you the sum of the k plus 1, all the k plus 1 terms. I know s sub k is actually equal to this. It's k, 2k plus 1. We assumed that that was true. The k plus 1 term, if I come up and look at my series here, the k plus 1 term would be what I get when I plug k plus 1 in here. Remember, this is a term number, not necessarily the sum. Here's the sum. Well, plugging that in here, I'm going to end up with 4 times k plus 1 minus 1. And now I just need to do a little bit of simplifying. So kind of backing up a little bit, trying to show s sub k plus 1. First thing I have to do is understand that that's the sum of the first k terms plus the k plus first term. The sum of the first k terms was something that we said we had to assume was true, and we got that from using this formula, just plugging in k here, because remember it's sum, so this is the actual sum part of it. These are a sub 1, a sub 2, and so on. Showing k plus 1, well, if I plug k plus 1 in here and simplify, that's what this is. So this is what I'm eventually trying to show that s sub k plus 1 is equal to. And how do I get that? Well, I get that by adding the first k terms together, which would be this, and then adding the k plus 1 term onto it. So now if I simplify, distribute the k, I get 2k squared plus 2k. Distribute the 4 and simplify, I get 4k plus 4 minus 1, so plus 3. Combine like terms, I have 2k squared plus 6k plus 3. Sorry, that should be 1k. This should be 5k. Knew something was looking weird. There we go. Need to learn how to distribute, I guess, better. There we go. K times 1 should give me just 1k. Alright, so I have a total of 5k. And now what I'm trying to do is this the same thing as that? In other words, can I factor this into that? Well, I can kind of cheat and just say, I'm just going to write down that that is, and then I'll FOIL to see if it works. Or if you remember your doing your little multiplying front and back numbers together, you can say 2 times 3 I know is going to give me 6. Factors of 6 that give me 5, it's going to end up being 3 and 2. And so then we would say it's 2k squared plus 3k plus 2k, or you can do those in reverse order if you want, plus 3. Factor by grouping. Factor out what the first one has in common. They just have a k in common. That would leave me with 2k plus 3. Second one doesn't have anything in common, but something has to get factored out, so you factor out 1. Those being the same means you did this correctly. That means that's one of the factors, 2k plus 3. And then the other parenthesis is what you factored out. It's k plus 1. And sure enough, that's exactly what we have. And therefore, we have proved by mathematical induction that that formula is actually true. Like I said, this is a little tricky and takes some time to get used to. This, when you look at the steps, the first step, that shouldn't be a problem. Plugging in s sub 1, that'll be very quick and easy. Writing down this step, assuming that this is true, that's usually not so bad. Need to figure out that you need to show this, and then that first step is usually the trick. If you can get by that, you'll be okay. If you need help, like I said, feel free to come in and ask for help, and I can help you out a little bit. All right, let's do another one, see if you can get a little more practice with it. Same thing, here's the formula this time. So again, I have to, step 1, show that it works for s sub 1. So the sum of the first number should just be 25. That's what I'm trying to show. Well, this is the actual sum formula. So if I plugged in 1, I would get 1 divided by 2 times negative 3 times 1 plus 53. So I know that I'm looking at 1/2 times 53 minus 3, or 50, and sure enough that gives me 25. So I've shown that the first number works. Now the second one, I have to assume, so assuming that s sub k is equal to, now remember what s sub k stands for, it's the sum of the first k numbers, so there's the first number, second number, third number, so on. Here's the k number. Now that means I'm plugging k in, because remember, to get 22 I would plug 2 into this formula. That's where that's coming from. So if I plug k in, it's negative 3k plus 28. There are the first k terms, and now the sum would be k times negative 3k plus 53 over 2. Writing it like that instead of saying n over 2 and then times that parenthesis. So assuming that this is true, I need to now show that s sub k plus 1 is equal to, again, this stands for sum, so I just need to plug k plus 1 in here. I don't need to necessarily write this out. I could just say s sub k is equal to this. It's sometimes helpful to write that out and understand how that works. So I need to show that s sub k plus 1, if I plug k plus 1 in here, I'm going to get k plus 1. Plugging k plus 1 in here gives me negative 3 times k plus 1 plus 53 over 2. And then, of course, I'm going to simplify that parenthesis that I have there. I have k plus 1 times, if I distribute here, I get negative 3k, negative 3 plus 53, so plus 50, all over 2. So I'm going to try to show that this is equal to that. So S sub k plus 1 I know is the sum of the first term, second term, third term, all the way up to the k plus 1 term. So it's technically this. A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, all the way up to the A plus k plus A plus k plus 1 term. Alright, so I'm showing a little more work than I did for the previous one to see if that'll help you out. Alright, so now I have to think about this. What would the sum of that be? The sum of the first, second, third, fourth, all the way up to the k. That would be the sum of the k terms. That's S sub k plus, I still have this A sub k plus 1, the k plus 1 term. I know what this is. We assumed it to be this. So I can just simply say this is equal to S sub k, which is k times negative 3k plus 53 over 2 plus, remember this is a term number, A sub k plus 1. This is how I get the term numbers. If I plug k plus 1 in here, I'm going to get negative 3 times k plus 1 plus 28. So negative 3 times k plus 1 plus 28. So there's the sum of the first k terms, which is what I have up here. And then here's the k plus 1 term when I plug k plus 1 in here. And now I'm going to simplify this and hopefully get it to equal that. If I don't, then I know something's wrong. Alright, so multiply out, that's going to give me negative 3k squared plus 53k over 2. If I simplify here, I'm going to end up with negative 3k, negative 3 plus 28, so plus 25. Now I need a common denominator, so I'm going to multiply by 2 over 2. And that's going to give me negative 3k squared plus 53k over 2 plus, it's going to give me negative 6k plus 50 if I distribute the 2. Now I've got the common denominator I'm looking for, so I should be able to add like terms together in the numerator. Gives me negative 3k squared. It's going to give me 47k plus 50 divided by 2. And now if you're not sure if that factors into this, you could easily distribute this out and see if it equals this to kind of make sure. Because the numbers are a little bigger, that might be a little tougher to see the factors. But let's look at this. If I distribute it here, that gives me negative 3k squared. And that's exactly what I have in front here. Obviously I've got the over 2 part. If I did the insides, I get negative 3k, outsides 50k. It's going to give me 47k. And if I did the last, I would get 50. So I can say that without actually going through all the steps and doing the factoring, I can say that I know k plus 1 times negative 3k plus 50 divided by 2 is what this is eventually equal to, what it'll factor into. And therefore I have proven that this is what S sub k plus 1 is equal to. Again, it takes a little time to get used to it, but hopefully the problems you get to practice will give you a little bit of confidence with it, and we'll spend a little bit more time on it tomorrow. But there is your homework help for section 9.4, day 1.